Okay, so like we said, Planck's ideas were going to change a lot of the ways we looked at our universe. Okay, so we started to revisit some stuff we had seen before. And wondered if we approached it with Planck's new kind of strange math trick, would anything else start to be explained or start to be explained in a different way anyway? Heinrich Hertz, you might remember him. Okay, he was the guy who, when Maxwell predicted the existence of these electromagnetic waves that propagated without a medium, a bunch of perpendicular electric and magnetic fields, right, going back and forth, generating one another. We didn't mention it at the time, but there was something else he kind of noticed that was interesting anyway, right? He noticed it, didn't really look into it that much, but it ended up actually being a pretty big deal, as we're going to see here, okay? Quick reminder of what Hertz's experiment was. He essentially had an induction coil, which was just a rapidly changing electric potential to make electrons jump back and forth. That was how he generated his changing electric field, which, as we know, a changing electric field will generate electromagnetic radiation. And then if it reaches a receiver antenna, you should see a spark in that antenna over there. So Hertz just wanted to see the spark better. He was doing it in a room full of natural light and all kinds of other light pollution, we would say. So he put it in a dark box so that the spark would be really clear to see. The dark box, though, had a glass window. Okay. Suddenly he noticed that the sparks got a lot smaller. All he hadn't changed anything about the experiment. He just put them in a dark box that had a glass window. Okay. So he kind of, well, that's weird. I just wanted to see them better. I didn't want them to get smaller. Right. He tried this again, but instead he just, on a whim, said, okay, I'm going to put them in a dark box, but instead of a glass window, let's just see what happens if I try a quartz window. And then the sparks got big again. They got back to their original size, or close to it anyway. Now, it came out that glass blocks ultraviolet radiation. So glass blocks UV radiation, but quartz doesn't. So from the sun, when you get a tan, that is because of its UV light. That is, UV light has a high enough energy to interact with the molecules in your skin and give you a tan, right? It interacts with the pigments in your skin and gives you a tan. So my point of bringing that up is that you'll notice you never get a tan on a sunny day if you're sitting inside, even if you're sitting at a glass window, right? Driving around in the summer, you don't really get a tan through your windshield because UV rays are blocked by glass. Hertz basically said, he kind of said, okay, it looks like the UV rays, it seems like, since the UV rays were being blocked by the glass and now the spark got smaller, looks like, I guess, for some reason, the UV rays are helping the electrons kind of pop off the material. So for whatever reason, UV rays that are bouncing around this room, because again, there was sunlight and everything, said, seems like, okay, for whatever reason, the UV seems to be helping the electrons jump off and make a spark. He kind of shrugged his shoulders, moved on, didn't think too much about it after that. This phenomenon actually was observed quite a bit. It actually became to be pretty well studied, not well understood, but pretty well studied. We started to really notice that, okay, it basically looks like EMR hitting a surface can sometimes, but other times not, cause electrons to be emitted from the surface. That's what we call the photoelectric effect. Photo, again, means light. And electric, do I really need to say what that refers to, right? Electricity or moving electrons. So it was very interesting. People were fascinated by it, but it went pretty unexplained for a long time. Okay. A lot of observations were made. We gathered a lot of data on it, but we didn't really know why it was happening. I'll show you an example, a similar example here, using basically a different version of an electroscope. So something is given a charge, okay, and then we'll see what happens when UV ray is incident upon it. So notice the UV rays appeared to remove or dissipate the charge, the negative charge that was built up on the electroscope, right? So when the UV rays are incident upon it, it seemed to be kicking off the electrons, getting rid of them so that the electroscope went back to being neutral. That's the photoelectric effect. Light comes in, electrons get kicked out. Cool. Now, like I said, not well understood, not fully really explained. However, a lot of data was gathered on it. So here kind of summarizes the information that we knew about the photoelectric effect at the time. It started to present kind of a problem, okay? But first, let's just see what the data was. So it appeared that all substances have a threshold or minimum frequency, okay, which must be met for the effect to occur. What's the effect? Well, the effect is knocking electrons off the surface of the substance. If you are below that frequency, nothing happens. So if you are light that has a frequency below this substance's threshold frequency, which every substance just has its own threshold frequency, it's just a property of the substance, okay? But if light is below that, it doesn't matter how much light you shoot at it. It will never cause the photoelectric effect to occur if it's not the right frequency light or higher. So what we're saying there is below F naught, the intensity has no effect. Think of intensity. You can think of it again, it's energy per second per area, so watts per meter squared, okay? But you can kind of think of that as the number of photons hitting it per second per meter squared, right? Because that's the energy. So, right? So, in other words, it didn't matter how many photons you sent at the surface if those photons didn't have the right frequency. Nothing would happen. No photoelectric effect. Now, above the frequency, if you were at the frequency or above, the intensity was directly proportional to the photocurrent. In other words, if the photons you were shooting at it did have the threshold frequency at least, well, then shooting more of them would cause more electrons to be ejected. Kind of makes sense, right? However, it has no effect on the kinetic energy of the electrons. So more will be kicked out, but they won't be moving faster or anything. They'll just be all getting kicked out. Again, above frequency, though, the frequency is directly proportional to the kinetic energy. So if you are at the threshold frequency, but then you send photons with higher and higher and higher frequencies, not only will electrons be getting kicked out, they'll be going faster and faster and faster when they're getting kicked out. However, it has no effect on the photocurrent, which again is how many electrons are getting kicked out. So just in quick summary, if you are at some frequency above the threshold frequency, you can kick out electrons. But if more of that light, more higher intensity is sent, it'll just kick out more electrons. It won't make them go any faster. However, if you're above the threshold frequency and you send photons with a higher threshold frequency, it won't kick out any more electrons if you keep the intensity the same, but it will make the electrons that get kicked out move faster, have a higher kinetic energy. Okay, here's kind of some graphs summarizing it. I want you to note before we jump in, all of these graphs kind of assume that the threshold frequency has been met. Okay, with the exception of these two, they kind of show where the threshold frequency has been met. So that is the threshold frequency. Here we're kind of saying that the threshold frequency was 0, or the scaling of this graph is misleading or something, okay? But notice the kinetic energy of the electrons, essentially how quickly they're moving, okay, is directly proportional to the frequency of the light, except nothing happens, no electrons kicked out. You hit the threshold frequency, and then if you continue to increase the frequency, you will kick out electrons, but you will kick them out and make them move faster and faster, okay? If you are at the threshold frequency and you increase how many photons you're sending, you increase the intensity now, right? It's not going to make the electrons move any faster. Okay. What it is going to do, I'm going to hop over here. What it is going to do is make more electrons get kicked out and therefore increase the electron current, right? Again, current is what it meant in unit 2 here. It's the same thing. It's still just the flow of charge, right? So, or the moving charges. Okay. And then jumping back to this one, though, if you're at the frequency, the number of electrons being kicked out, their electron current, won't change by increasing the frequency. All that'll happen is you'll make them get kicked out faster and faster by increasing the frequency, but you won't change how many are getting kicked out. Okay. Again, those graphs all kind of assume that the threshold frequency has been met. These ones are these are the more accurate ones because you increase the frequency, increase the frequency, increase the frequency, nothing's happening, and then boom, you hit the threshold frequency and suddenly you have a current, okay? If you keep increasing it, nothing's gonna happen to the number of electrons, right? Just what's gonna happen is they're gonna have more energy when they do get kicked out, okay? And like we said, different materials have different threshold frequencies. So it is harder, you need a higher frequency to kick electrons out of copper than you do out of cesium. It's just a characteristic of the metal that you're looking at. Just to kind of visualize the photoelectric effect, let's take a look here. So notice I have the frequency in about the red range, okay? If I turn up the intensity, okay, so right now it's off completely. If I turn it on, okay, now I'm sending photons and they're hitting the surface. I can turn it up all the way to 100. So what does that tell you about this frequency compared to the threshold frequency of this metal? Clearly, this is not a high enough frequency, right? The wavelength is too high, so the frequency is too low. Let's increase the frequency. Okay, so what did we just hit? We just hit the threshold frequency. Notice electrons are now being kicked out. Okay, you'll notice these plates have the potential to be charged. We'll get to that in a sec. Right now, they're just kind of boop and flying over at their own ease. We could put an electric field here, and we will. Okay, now I'm going to keep increasing the frequency. I'm not going to change the intensity. I want you to take a look at the number of electrons as I go and the behavior of them. What do you see? Does it look like there's more electrons coming? It shouldn't, right? And it doesn't. It doesn't look like there's more electrons coming. What are they doing differently, though? Right, they're moving slower. They have a lower kinetic energy. So no more photons are getting kicked out. It's just that the photons that are getting kicked out are moving faster. Okay, let's put it back to the threshold frequency-ish, which is about green light. Okay, and then let's bring the intensity down. So now I want you to watch the behavior of the electrons. Okay, so get a good idea for the number. Now I'm going to bring them down. Okay, what does that mean? It means I'm not sending as much light energy or as many photons. So are the electrons moving any differently than they were before? Are they moving any slower or faster? No, but what's different about them? Just fewer of them are leaving, right? If I bring the intensity down more and down more and down more, the electrons are always, a few electrons are always leaving, okay? They're always leaving at about this speed that they're going here, just not as many of them are doing it because not as many photons are incident on the surface. Bring it all the way down to very low. As long as there's a few photons hitting, we should see a little bit of photoelectric effect. Oh, there goes one, right? Okay, still moving the same speed. Of course, if I turn the light off, well, now there's no photons hitting the surface. So now there can't be any electrons being ejected. Okay, bring the intensity back up to about, I don't know, whatever, 66. Okay, if I go well below the threshold frequency, now the same number of electrons are coming out as were green at this same intensity, right? It's just that what do? They move faster and faster and faster, but no more electrons are being ejected. How could I make more electrons be injected? Well, hit it with more photons. In other words, crank up the intensity, right? And sure enough, now I get fast electrons and a lot of them. But I could bring that intensity down, still have fast electrons, right? They're still going to be going just as fast. There's just not as many of them. So we made these observations. We studied this fairly well, right? It was puzzling. People were kind of weirded out by it. It presented some problems, but no one had really explained it. Someone was about to come along, an unknown physicist, who was going to attempt to explain it. And he was going to do that by applying Planck's ideas to it. And that unknown physicist was Albert Einstein. Did you know Albert Einstein in his lifetime won one Nobel Prize? He gave us the theory of relativity. He gave us mass energy equivalence, which is coming up later. Okay. He gave us a lot. And the one Nobel Prize that Albert Einstein won was actually for his work on the photoelectric effect. So remember, even Planck did not think that his quanta were a physical reality. It was just a weird trick that made the equations work. Planck thought at most it has something to do with the way that light interacts with matter. So it's not like really energy is discrete. He thought it's just the way that light can impart its energy for some reason is discrete. Something's going on when light interacts with a particle, and that process seems to be maybe quantized, okay? Or at least appears to be quantized. He definitely did not think that anything to do with the light itself was quantized. Already, even Planck's math tweak here was a little strange, right? Should be. It should feel strange. I don't blame you, okay? Einstein took it a step further. He said, no, the light energy itself is quantized. He's saying this is not some weird math tweak. This does not just have something to do with the way that light is interacting with matter. The light is actually quantized. Energy is actually discrete. There is a smallest amount of energy that you cannot go smaller than for a given frequency. This idea was the basis for his explanation of the photoelectric effect. So he took the photoelectric effect and said, what if we go quantum on it? Now, let's review. The photoelectric effect only occurs if the incident light is above a certain frequency. Okay, and therefore energy. Why therefore energy? Remember, Planck had shown that the energy is directly proportional to the frequency. Different materials have different threshold frequencies. Now, no matter what the intensity is, as we just saw, no matter how many photons you send, and also no matter how long you send photons at it, no electrons will be ejected if the light does not have at least the threshold frequency. Okay. The other weird thing that couldn't be explained with classical physics was that electrons are emitted almost instantaneously. It just happens. If they're going to be emitted, it just happens right away. Okay. There's never a waiting period to see the photoelectric effect. It happens or it doesn't, but it never starts happening if you wait long enough. What's the issue here? Why couldn't classical physics explain this? Well, waves transfer energy continuously. If the wave isn't delivering enough energy right now, just wait longer. The wave will continuously transfer energy to it. It will build up, it will build up, it will build up. Okay, so given enough time and a high enough intensity, any amount of EMR behaving as a wave should eventually cause electrons to be emitted. Maybe you're going to have to wait a while, but it's continuously transferring its energy, right? You can think of it as the wave is coming in, getting the atom excited, 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 excited. And once it's transferred enough energy, boom, off pops an electron, photoelectric effect. That is how these waves should behave. As we've seen, that's not how the photoelectric effect works, right? How the photoelectric effect works is bang over, it happens or it doesn't. It's a one and done, it's an all or nothing. It's going to eject an electron or it's not. So particles transfer energy in one burst as they collide, and either they have enough energy to cause a change or not, right? Exactly what we see in the photoelectric effect. Think of it this way, the difference between particles and waves, right? Imagine I have some infrared rays. If I have like a heat gun, an infrared ray, and I hold it on you, continuously it's going to transfer heat to you and transfer heat to you and transfer heat to you. And you're going to get warmer and warmer and warmer and warmer. And eventually you'll get too hot and say, hey, stop pointing that infrared gun at me, right? That is wave-like behavior, continuously transferring energy. To imagine particle-like transfer of energy, you're pretty used to this, right? If I threw a bunch of little cotton balls at you, right, none of them are going to knock you over. I could keep doing it and keep doing it. I could get 100 million cotton balls and I could throw them at you a whole bunch really fast, throw as many as I possibly could, right? Even get all my friends to help just pelt you with cotton balls. It doesn't matter how many cotton balls you get hit with, they're never going to knock you over. They just don't have the energy to do it. Doesn't matter how many times you get hit with a cotton ball, you're not going to fall over from it, right? But if I go get a medicine ball and whip it at you, right? All it takes is one then, and you're going to get knocked over. Now, think about this on a larger scale, because that's talking one electron. Let's talk about a whole bunch of them, okay? If you as a class all line up and I start throwing a few cotton balls at you, nothing's going to happen, right? You're never going to fall over. If I increase the intensity and throw more and more and more and more cotton balls, still, none of you are going to fall over. If I crank up the frequency, the energy, in this case, that means using a bigger ball, a medicine ball now, and I start throwing, if I throw just a few, if I just throw just one, that hits one of you students, you're going to get knocked over probably, right? How do I knock over more students? How do I knock out more electrons is what I'm saying, right? Well, I increase the intensity of this new particle with a higher energy, the medicine ball. I increase the intensity of that. I throw more and more medicine balls and I'll start to knock over more and more students, right? Clearly, that models the photoelectric effect pretty well. And yet we're talking about particles. Cotton balls and medicine balls are particles. So in the photoelectric effect, there's really no explaining it without light being a particle. So why are we talking about this in the context of light that we've just spent all this time saying has to be a wave? Well, light is a particle. So in the photoelectric effect, there is no explaining it without light behaving as a particle, okay? The photon. It just does not work. But in the double slit experiment, I wasn't lying. Okay, I haven't just been lying to you for the last couple weeks. The double slit experiment proves without a doubt, because particles don't interfere, and the double slit experiment shows clear interference patterns, light is a wave. It must be a wave. Double slit experiment, light must be a wave. So, which is it? Well, like a lot of quantum mechanics, okay, the answer is true, but it's weird. You might not like it. Right now, light is both a wave and a particle. More specifically, okay, with a little more explanation, light has both wave and particle properties, and it will act like one or the other depending on what slash how it's interacting with, right? So depending on the interaction it's in, light will behave as a wave or as a particle. For example, in that infrared heat ray gun, that was light acting like a wave. It was transferring energy to you continuously. But in the photoelectric effect, it is clearly transferring energy all at once or not at all, like a particle. Okay, so we treat it like a wave and we call it a wave when it's acting like a wave. We call it a photon when it is acting like a particle. Welcome to quantum mechanics. Okay, so I will introduce the basics of the math. However, for the more numerical examples, I will make a separate video with those. I'm going to, for the most part, keep the theory and explanations in one video and then the kind of examples in another video so you can know where to go for what. Okay, so the basic math, it really is basic. Yes, we're venturing into kind of strange territory here, but this strange territory is actually, in a lot of ways, coming from the most basic ideas, like the conservation of energy. So all we're doing here is conservation of energy for these equations, okay? So the energy in the photon during the photoelectric effect is going to be converted into two things, or one thing if it doesn't have a high enough frequency, but two things max, okay? The first is the work needed to remove the electron from the material. So it takes some work to just get the electron out in the first place. Hey, does that give you any ideas about maybe what the threshold frequency was all about? Why it was never removed below a certain frequency? We'll come back to that in a sec, okay? But then once you've done that, once you've removed it, any leftover energy from that photon will now become the kinetic energy of that ejected electron. So the leftovers go to the kinetic energy of the electron, okay? So again, just conservation of energy, physics principle number 5. All the energy initially equals all the energy finally. And we often sometimes say E in because there's an incoming photon with an energy has to equal E out, okay? So the E out is made up of the energy absorbed in releasing the electron and the kinetic energy of the electron. So if you've got some left over after you do all the work needed to free the electron, well, now the electron will be able to have some kinetic energy. So the incoming energy is in the photon, right? And we find it using Planck's equation. So just E equals hf if you're given frequency, or E equals hc over lambda if you're given wavelength, okay? The atoms absorb some energy from the photon. This is the minimum amount of energy they must have to be able to free the electron, okay? And we call it the work function. So this is, that work function is the amount of energy that a given substance, every substance has a different work function. For example, sodium's is different than cesium's, but that work function is a property that says, how hard is it for me to get my electrons kicked out of me, okay? It's related, it's not the same thing, but it's related to the ionization energy from chemistry or from physics. We talk about ionization energies too, okay? Worth noting here, the work function, like we said earlier, explains the threshold frequency, right? So we have the energy of a photon. What's the work function? It's the energy of a photon that has just the threshold frequency. So if you just have the threshold frequency, all you do is overcome the work function and you can free an electron, but what will that electron's kinetic energy be? 0. All you're going to do is just barely kick out an electron, right? When a photon is at that threshold frequency, it has just enough energy to overcome the work function. Note that this relationship is on your data sheet. Okay, but again, if the photon does not have at least the threshold frequency, well, it doesn't have enough energy to overcome the work function and it does not free an electron. It either has it or it doesn't. Particle-like behavior. And once again, the electrons that are smashed out by the photon have any extra energy that was not used to overcome the work function, leftovers. Okay, what's the kinetic energy of a massive particle? It's 1/2 mv squared. So this guy here is really, I think of this as the photoelectric effect equation. This is not on your formula sheet, okay? It's just an application of the law of conservation of energy, okay? How to get this is HF and HC over lambda is on your data sheet. How to get this is on your data sheet. You probably have it memorized by now from Science 10 days even, right? MV squared over 2. And the work function is also on your data sheet. However, it's up to you to understand the physics behind the concept to know that the energy of the photon is going to be the work needed to remove it, plus any leftovers will go to being the kinetic energy of the electron. So I'm just going to do these examples here because this really gets into what the photoelectric effect is, what's going on in the photoelectric effect, and then I'll make another video for the examples on the coming pages, okay? So light with an energy of 1.7 electron volts is incident on a metal which has a work function of 0.9 electron volts. With what kinetic energy would the electrons leave? Okay, so it's just the conservation of energy. So we could say E in equals E out, okay? Okay, the energy in is just the energy of the photon, so we can say E P for photon. What's the energy out? What is that photon going in to become? Well, some of it's going to get used up to overcome the work function, and any leftovers are going to become kinetic energy of the electron. So in this case, we were just given the energies. So we want to know the kinetic energy. So just going to add an H there because it kind of looks like potential energy. Okay, so the kinetic energy of the electron will be, let's see if this makes sense, the energy of the photon minus the work function. Well, yeah, totally, right? The kinetic energy that's left over for the electron is just what's left after you take from the photon the energy waste, well, quote unquote, wasted on just removing it. So normally when you see electron volts, right away convert to joules. However, do we need to here? Not necessarily, because we can get our kinetic energy in electron volts. That's still a unit of energy. Nothing wrong with that. So the photon had an energy of that. It used up this much to just get the electron out, meaning that how much was left over for the electron? I got 0.8 electron volts. Okay. Now I didn't get away with it. I still have to convert those electron volts to joules because to find their speed, right, we're working in standard units. Your speed will not be in meters per second if you tried to use electron volts. Okay, so let's not mess around with that. So I got converted 1.28 times 10 to the negative 19 joules. That's how much kinetic energy this electron will have after the photon has been destroyed and transferred its energy to the work function and to this little electron. What is the speed of the electron? Well, it's a massive particle. Okay, it still just has some kinetic energy. Its kinetic energy is still just that thing. So manipulate for speed, not velocity, speed, because it's energy, scalar. Okay, and the mass is the mass of an electron, of course, because that's what we're looking at, the kinetic energy of an electron. I got that it would be moving at, so pretty fast. All right, let's look at this next one. A metal has a work function of 1.5 times 10 to the negative 18 joules. Light of 1.2 times 10 to the negative 18 joules is shown. So that's the energy of the light, the energy incoming, right? With what energy do the electrons leave? I want you to think about this one for a sec. Take a look at those numbers. You see it? Tricky, tricky. Do the electrons leave? Nope. This is not enough energy to overcome the work function. This photon will get absorbed, it will get destroyed, but all it's going to do is end up heating up the metal a bit. That energy is just going to be absorbed by an atom. It will not spit out an electron. This is a cotton ball, not a medicine ball. So if you didn't notice that, that's okay. If you go to do the calculation, you'll get a negative kinetic energy for the electron, which of course is not a physically meaningful thing, but it does tell you that, oh, the electron has negative kinetic energy. Well, that means it didn't have enough to overcome the work function, right? It was, in fact, that negative tells you how much more energy it would have needed to have to overcome the work function, right? How much energy was it missing? So just with pure theory, the incoming energy is not enough to overcome the work function. So what kinetic energy do they leave with? Trick question. They don't leave at all. So we've really entered quantum mechanics here. Light is a particle Light is a wave. It has properties of both. And so I guess old Newton wasn't so wrong after all. Okay, so I'm just jumping ahead to page 13 in the notes here a little bit because this really is part of the theory and the introduction. The examples in between here and there will be done in the examples video, but I wanted to introduce this idea in the theory video, okay? So we've been talking about the kinetic energy of the electron based on the incoming photon and the work function. How do we actually know how fast this electron is going to see if this equation actually does work, right? Because it all kind of depends on the kinetic energy of that electron, whether or not this makes sense, what we're doing here, right? Well, Millikan's back, okay? Millikan, who showed quantization of charge with the electron, remember that, right? Quantization of charge with the oil drop experiment, okay? So quantization back then, right? Remember, it was the charge has a minimum amount that it cannot be broken down any further below. That's this same stuff, quantization. So Millikan used an apparatus. It's pretty clever, okay? So essentially what this is hooked up to a battery and an ammeter. If an electron makes it across, a current will be registered, okay? But what he did is hook up a power source to give this plate a negative charge and give the plate where the UV lights are coming a positive charge, right? And so when an electron gets kicked out by the incoming photons, it actually, what force will it feel? It'll want to go back, right? It doesn't want to go to this negative. It doesn't want to go, it wants to go back to this positive. So I'll show you what this looks like in action. So back to this simulation here, okay? Again, let's just get some going, okay? Notice there's no potential here, right? The electrons are just kind of, and then Newton's first lawing across here, right? No acceleration, nothing like that. We could make that plate positive, right? And then you notice the current pops up a lot, right? Those electrons are now going. Let's try bringing it down. So again, back to zero where there's no potential difference at all. They just Newton's first law across, right? Law of inertia across. If we make this plate like Millikan did, negative, right? Notice some of them even get repelled all the way back and reabsorbed back into the metal. Okay? And you'll notice as I increase the wavelength, which is decreasing the frequency, right? Which, as we know, will lead to lower energy electrons coming out. Notice some of them actually don't even make it. A few of them do, right? But still, but only the highest energy electrons are now making it. I can continue to decrease the energy of the electrons until the point where, right, I just barely get no electrons at all making it. So now, even the maximum kinetic energy that these guys could have is not quite enough to make it across, at least to produce any significant current. I know it looks like some of them are making it. Okay. Right? So we don't allow them to come. If I go high enough, it doesn't even get close, right? This would be too far. But we can find the voltage, though, at which some, oh, now we're below the work function, okay? With these green ones, they don't even get close to enough kinetic energy. These photons are not imparting enough energy on them to even get close. So I need to lower the voltage, give them a little bit more of a chance to make it across, right? In fact, I might not even be able to find this one. It might be so low, okay? Well, maybe, no, still zero current. Maybe if those guys make it. This is actually probably perfect. This would be what we would call the stopping voltage. Why do we call it the stopping voltage? Because the electrons with the highest kinetic energy are just barely not making it. So realistically, what you do is you find the voltage, the potential difference at which it just barely becomes zero. And you say, okay, at this voltage, when I make this plate negatively charged and that plate positively charged, with that potential difference, the electrons just don't make it. So we found the maximum kinetic energy that we are able to eject them with this frequency of light, right? So the electrons will be repelled by the negative plate at the opposite end, and then you can slowly increase the voltage until only the most energetic electrons are able to make the jump and generate photocurrent without being sent back. The point at which zero photocurrent is first observed is therefore known as the stopping voltage. It allows us to determine the maximum kinetic energy of the discharged electrons. Why the maximum kinetic energy? Why don't we just say the kinetic energy? Well, you got to remember some electrons are not just going to boop right out and no waste, right? They're going to bump around, they're going to hit each other. So the most energetic electrons are the ones that kind of have a nice, easy, free path. They get lucky, they get knocked out, and they really don't lose any energy on their way across the vacuum tube. So yes, the photons do impart all of their energy to the work function, and then any leftovers go to the kinetic energy of the electron. It's just that some of that kinetic energy of the electron will now get kind of wasted as it bumps into other stuff, loses heat, whatever, okay? But the max kinetic energy can be found, hey, with our old friend QV equals a change in energy, right? If you find the amount of energy that you need to take away from the most energetic electrons, then you've found the maximum kinetic energy of the electrons, right? So this is given as a separate equation on your formula sheet. I don't even think it should be, honestly, but sure. Okay, it's just our old friend, but applied now to the photoelectric effect. Okay, so once again, the energy that you take away from them with that applied electric field, when you just start to stop every single electron, well, now you found the max energy they have because you're taking it away from even the most energetic ones. Okay, so how does that actually look? Let's just do this example. I'll do the other one in the example video. But radiation with a frequency of 7.52 times 10 to the 14 hertz illuminates a photocell with a work function of 2.2 electron volts. What voltage would be required to reduce the photocurrent to zero? So essentially it's saying what voltage is going to take away whatever kinetic energy they've been given by this photon. So to figure that out, okay, so as always, E in is equal to the work function plus the kinetic energy of the electron, except we know now that the kinetic energy of the electron, of the most energetic electrons, is equal to Q phi stop. So then moving stuff around. And that's it. Okay, now we're ready to plug in. Whoops, convert this to joules. All over Q, this is an electron we're talking about, so, and I got that the stopping voltage, so the voltage necessary to take away all of the kinetic energy that it got from this photon is 0.916 volts. More examples will be in the example video. There's tons of examples in the notes for this, okay, from page 11 up to page 20. But the main theory here is that we have now seen very strong evidence for light acting as a particle, right? Albert Einstein, with the photoelectric effect, said light itself is quantized. That's the only way to explain the all or nothing nature of the photoelectric effect. Okay, maybe try out some of the examples in the booklet, see how you're feeling with it. If you're stuck on one, then you can pop over to the examples video lesson and see how I do it. If you're just looking for practice, check the Google Classroom or agenda for which formative questions go with this stuff.